Hello everyone. In this video we're going to continue talking about nonlinear functions with our second type of functional form, the polynomial. Let's start by considering an example. Suppose we were to run a regression of wage on age. If we did this, what do we think that the sign of beta 1 would be? As you get older, you get more experience, more education, all those things that are going to help you earn more money. So beta 1 is probably positive. But as I discussed in the previous videos, this linear equation assumes that beta 1, the effect of age on wage, is constant throughout your entire life. But that's probably not the case. Certainly when you're younger, as you get older, wage is going to go up, but most people have a career that eventually peaks out, and as they get older, their wage might stop changing, or it changes more slowly, and eventually people might start cutting back their hours, working less, so their pay is going to go down. What we learn from this is that reality is nuanced. Nuanced in a way that a linear equation can't capture. Our goal here is going to be using polynomials to get a little bit more nuance into our regressions. We're going to load up a dataset, ACS 2014, which is data from the 2014 American Community Survey. This is a survey that's randomly sent out every year to people and collects all kinds of information, including wage and age. So we're going to run that simple regression and see what we get. Over here in Excel, we will go back to Data Analysis and run a regression. Our Y range, or left-hand side variable, is going to be wage, and then our explanatory variable is, of course, going to be age, the only other variable we have. Make sure labels is still checked, click OK. Looking at these results, we have a slope of $586, meaning we estimate for every year of age, wage goes up by about $586. With a starting point of just short of $18,000. Looking at the regression line that results from this, we have a slope of $586, slowly going up throughout your whole life. But if we look at the data, what we see is there's some shape to this that's not necessarily linear. So how can we improve our regression to capture that shape? One way to do this is by moving to a quadratic functional form, essentially turning our regression line into a regression parabola. To do this, we need to add an age squared term into our equation. When we move to the quadratic form, it's important to point out that we have to keep the original age variable in there in addition to the new age squared. This is going to allow our function to take on any possible parabola with the intercept, the linear term, and the squared term. I'll point out here that it's usually of little harm to try quadratic forms if you think that that relationship might be there, because the worst that could happen is it's not significant and you just drop it and move on with your life. And you can do the same thing adding cube terms and so on. We'll look at those in a minute. Let's go back to Excel and implement this. I'm going to insert a new column right in here. I'll call it age 2 for age squared. And I'm simply going to take our age here to the second power and then fill that all the way down. We'll run a regression now, where our dependent variable is again going to be wage. I'm going to need to reselect that. And then for the explanatory variables, I'm going to select both age and age squared. Run the regression. What we get here is a large positive number for age, the linear term, and then a small negative number for age squared. If we think about the effect that this will have, initially we have a positive slope because we've got this really big number here and small number here. But remember that as age goes up, age squared goes up even faster. So this negative effect is going to get stronger and stronger and stronger as you get older, and eventually it's going to overtake the positive effect. So there's going to be a certain age where wage caps out and then it starts to drop. Looking at the scatter plot here, I've now plotted our regression parabola based on the estimates. You can see that our wage is increasing as you get older, but at a slower and slower rate until about the age of 50, and then it starts to drop off. Now, our regression was not perfect. Notice at the far end, we've got our wage actually dropping below the 0 line, which of course is not realistic. You can't earn negative wages. But as you can also see, this is not that big of a deal because there's only a handful of people here still in the labor force around 90 years old. but it does tell us maybe we can do a little bit better. Before we move on, let's do a little bit of analysis of our estimated equation. I've written it out here from our Excel results. We could now plug in age into this equation and predict a person's age. We can also figure out what is exactly the age that we think that wage will peak. This is a parabola like any other, so how do we find the top of a parabola? Well, we can take the first order condition. So I'll take the derivative of wage hat with respect to age. The derivative of negative 65,000 is just 0. The derivative of 4,883 times age, well, age drops out and we get 4,883.99 minus, now we have age squared here, so we're going to multiply everything by 2. We'll get 2 times 48.9231 times age. Remember that the 2, subtract 1 from that, just get 1. Set it equal to 0. And now we can solve for age. I'll get 4,883 equals 2 times 48.9231 age. Divide both sides by 2 times 48.92. And that's going to tell us the age where wage peaks. We'll go back into Excel to actually calculate this thing so we can be as precise as possible. So to calculate the age where wage is highest, we're going to take 4,883.99. We're going to divide it by 2 times, and we added to both sides, so negative of this. And that tells us it happens at 49.9, or about 50 years old, which confirms roughly what we saw from the graph. You might find yourself in a situation where the quadratic form doesn't give you quite enough nuance that you need. And if that's the case, you can always add more terms. We can add an age cubed term, age to the 4th term, and so on. Each term you add is going to give more shape to the curve. But at the same time, there's diminishing marginal returns to adding more terms. So how do we know how far to go with this? One thing you can do is compare how much does the RSS go down as you're adding more terms. If it doesn't go down by much at all, then you haven't really added much. Alternatively, you can see this as the r squared goes up as you add terms. If the next term you added does not change things very much, then you might want to stop there. There's no one right or wrong answer to this. Let's look at what happens to our wage-age regression as we add more terms. Here you can see a table where I have run all these regressions, adding in age to the 3rd and age to the 4th as we go to the right. So the first column you see, this is our linear equation. You can see this is the first equation we ran in this video, where the slope was $586. Next you can see the quadratic, which I also ran. Comparing the r squared, you can see that it goes from about 2.7% to 7.4%, so that's a large increase, almost 3 times as high. When we go to the cubic, we can see that it adds about 0.1% in the r squared, and then to the quartic, it does go up, it's just small enough that we can't see it with this level of precision. Looking at how these appear on a graph, you can see the starkest differences between the linear and the quadratic. Going from this blue line to the red parabola, there's a huge gain in terms of fitting this data. These don't look anything like each other. Now when we go from quadratic to cubic, the cubic is the green, there's some difference, but more or less they look pretty similar. You can see, though, that this does solve our negative prediction problem, which is good. And then when we go to the quartic, the gold line, it's almost on top of the cubic green curve. So we can conclude from this that the age to the 4th term is not doing a whole lot in terms of improving our predictions. And you can probably get away with the cubic model in this case. But again, there's no hard rules on that. Let's wrap up by looking at one more data set. This is a data set that I've just made up that shows a hypothetical relationship between exam grades and hours spent studying. We're going to look at this and think about why we might want to use a quadratic functional form here. I'm going to create a scatter plot by selecting our data and then insert scatter plot. We can see here that it looks like the relationship between studying and grades is not quite linear, and we can see that there is a little bit of a drop-off there. And if we think about studying and grades, that the more you study, the higher the grade tends to be, but there are diminishing marginal returns. Eventually, you know most of the material, and a little bit more studying is not going to be as valuable to somebody who's already studied for 5 hours as opposed to somebody who's just starting out. Let's run some regressions. First, I'm going to create a squared term for studying. I'm going to select this cell right here, square that, and then run this formula down. We'll run a regression. First, of the linear model, so I'm going to select grade as the y and as the x, just the original study variable. We can see that for every hour of studying, we predict about 7.6 points gained. Now, if we go back and run it again, we can do this with the grade variable as the dependent again, but instead for the x range, we're going to select study and study squared. And what we get again is this large positive number for study and a small negative number for study squared, which implies we have a diminishing return situation, much like we did in the age and wage example. In this graph, I have plotted that predicted parabola on top of the data. Now, one thing to point out here is that this is a parabola, but it doesn't quite look like a full parabola because it never actually starts to come down. And that's completely okay. In reality, we probably don't think that more studying would eventually start to lower your grade, and it doesn't here because the parabola just gets cut off. So keep in mind that using a quadratic form does not necessarily imply that we will see things start to reverse direction, because it could be that we're just zoomed in on the graph like this. That brings us to the end of this set of videos. We've covered two different types of nonlinear functions. We did logarithms in the last two videos, estimating percentage changes, and multiplicative regressions, such as the Cobb-Douglas function. And in this video, we built some nuance into our models using polynomials. If you have any questions about what we've covered here, please let me know. Thanks for watching.